Okay, here we are, another equilibrium problem. In this case, let me pick a color and a pen here. In this case, let's see, we're given a certain amount of IBR and we place it in the flask. It's in the gas phase. We have this reaction here, and we're given an equilibrium constant. Equilibrium constant in Kp. So that means that if we want to use Kp, we should probably express concentrations in terms of atmosphere. Or if we wanted to express concentrations in terms of molar, we would have to change this Kp into a Kc. All right, well, let's just go ahead for fun and keep it a Kp, and so therefore our concentrations will be expressed in atmosphere. So we're given essentially an initial amount of IBR, and we're asked to calculate how many grams of IBR remain after equilibrium is established. All right, well, let's just start right out and write down our ice table. 2 IBR, here's the equilibrium, goes to I2 plus BR2. All right, make the rows in the ice table. First row here is the initial concentration, then the change, and then the equilibrium concentration. All right, as we said, we want to express concentrations in terms of atmosphere because we're going to use Kp. So let's see if we can do that. Let's go back to the problem here. We're given grams. We convert that to moles. Here we have 1 liter. We have a temperature. Let's assume that IBR gas is an ideal gas. So we can use PV equals nRT in order to calculate what the pressure will be. So the pressure will be equal to nRT over V, assuming ideal gas behavior. Number of moles, well, 2.07 gram. Look up the molar mass of IBR. Turns out it's 207. How convenient. So there's a number of moles. R 0.0821 liter atmosphere per mole Kelvin. Temperature 150, but that 150 was in Celsius. So we're going to have to convert that to Kelvin plus 273, and then we're going to divide by the volume given in the problem. It was 1 liter. So put that in our calculators and we come out to 0.387 atmosphere. All right, so we have a number for our ice table, 0.387 atmosphere, and according to the problem there was no I2 or BR2 present. Let's see. Well, we can make this minus x. In that case, this will be a half x. Don't like the half, so how about making this 2x and making this x and this x? So when we solve for x, we're going to have to multiply by 2. Then at equilibrium, that should be a minus 2x. At equilibrium, be 0.387 minus 2x. Here we have x, and here we have x. So let's go ahead and write what Kp is. That will be the pressure of IBR, no, so I2, sorry, pressure of I2. Let me use the eraser function. There you go. Erase my mistakes. That's kind of cool. Pressure of I2 times the pressure of BR2. Okay, that's what the equilibrium expression is. Divided by the pressure of IBR squared. So the pressure of IBR. All right, so that's what the equilibrium expression is. Let's write down some numbers. In the problem, it was given that the Kp is 8.5 times 10 to the minus 3. That's equal to x squared over concentration of IBR, the pressure of IBR, 0.387 minus 2x, and we have to square this whole thing because we have a 2 as a stoichiometric coefficient. All right, let's go to the next page here. Let's solve this for x. Well, actually, let's go back here. Let's use the successive approximation. There, you could use a quadratic formula here if you wanted to, but just for fun, let's use the successive approximation. So that means we're initially going to put x equals 0. We're going to ignore 0. So let's write down that equation, 8.5 times 10 minus 3. that's equal to x squared, and we're going to ignore x, so this would be 0.387, and again it's squared. So x will be equal to 8.5 times 10 to the minus 3 times 0.387 squared, and we'll take the square root of that. And that's what x is. I solved this equation for x. We put those numbers into our calculator, we get 0.032. Alright, so that's the first value of x. And for the successive approximation method, we're going to put that in there where we ignored x, so we're going to subtract that from that. So let's just do that. X here is equal to 8.5 times 10 to the minus 3. That's that. Now we're going to say 0.387 minus this new value of x, 0.032. And this is going to be squared. Don't forget the squared. And we're going to raise this to the 1/2 power. X in this case comes out to be 0.026. We do it again. Now put that into there. We do it again. We have x is equal to 0.027. And we do it one more time. We have x is equal to 0.027. So this successive approximation seems to work. We did it once, we did it twice, we did it 3 times, we got convergence. So that's the value of x. Now we're going to go back, and the problem asked not what the value of x was, but how many grams of IBR remained after the equilibrium was established. Alright, so what do we have here? This is x in atmosphere. Remember, we put everything in atmosphere. So that if we subtract this off from our ice table, multiply it by 2 and subtract it off, that will give our pressure in atmosphere. And then we could use the ideal gas law to find out how many moles and then how many grams and so on. So let's actually do that. All right, so the final pressure of IBR is the initial pressure, 0.347, minus 2 times x, which was 0.027. Remember that from the ice table? So the final concentration is 0.387 minus 2x, and we solve for x, so we have to multiply by 2 before we subtract it. So that's the pressure. It comes out to be, let's see, 0.293 units there are atmosphere. Now I want to convert this to moles and then to grams, because the problem asks how many grams are remaining. This is the pressure that remains from IBR. Well, N is equal to PV over RT. Now let's dispose of the units for now. 0.293, 1 liter. R is 0.0821. T, 150. Plus 273 in order to convert it to Kelvin. So the number of moles is, let me check my numbers here, 8.44 times 10 to the minus 3 mole. That's how many moles. To convert that to grams of IBR, we multiply by the molar mass. This number of moles times 10 to the minus 3 mole. Molar mass, we said, was 207 gram per mole. So this comes out to be 1.75 grams. Okay, so we started with 2.07 grams. It reacted according to this reaction, and after the reaction reached equilibrium, we have 1.75 grams of IBR left. Okay, there it is. Thanks for listening.